So let's get started, get back again. So our next speaker is Albrecht Schwarz. Albrecht Schwarz is from ETAS, is a Robert Bosch company. He's working as a system architect and system engineer for distributed information and computation and communication system. He received his PhD in electrical engineering from the University of Stuttgart. Albrecht also worked a long time in the telecom industry. So he worked for Alcatel, Lucent, and Nokia. So he brings a lot of concepts also from this industry now to automotive. I am working since a couple of months with him together, and I have to say every discussion I have is very fruitful and a lot of new input. This is exactly what we need if we want to organize better our networks in the future, and especially if we want to control our data and manage them. I think he can contribute quite significantly to this. Albrecht, I can't wait to hear your presentation.
Okay.
The floor is yours.
Thank you. So, good afternoon, everyone. I'd like to present now ideas about a solution for management architecture for software-defined vehicles, which uses management technologies from the ICT, Young as data modeling language, and NetConf as management protocol. So we've just heard in the previous session OpenFlow. So now you would have to replace OpenFlow by NetConf. The development of such an architecture, the engineering of such an architecture, demands to go through a couple of items. And, So before that items, I'd like to look at a software-defined vehicle for the entire life cycle of development and operations, and look actually what means dynamic management. When we look, we have used AUTOSAR as an example of an in-vehicle information system. AUTOSAR is something like a closed ecosystem, but a software-defined vehicle should be open, standardized. So this is a rather challenging task, how to show how AUTOSAR could evolve in that direction. And then we go through requirements, use cases, till we find a functional and logical architecture. We don't go in the technique. Now, we are looking at a software-defined vehicle in its entire life cycle, means development phases and operational phases, from the perspective in operating and management such a system. Don't be confused with all that text. Don't try to read it. We have overloaded the slides with information for the conference proceedings, so we have much more information later on. So first of all, below we have our in-vehicle information system. On the top we have that famous 8 denoting development operation life cycle model. So we are starting with our in-vehicle information system, and now the first step is we are complementing that information system by a management plane, because this is one major item which comes into the game when going in the direction of a software-defined vehicle. So that development and operations life cycle, if you unfold it, there are activities, development specific and operation specific, like here just plan, code, test, build, release, deploy, operate, and monitor. We have also now, besides the main actors of a development, now an operator or manager. In the previous talk we have heard about a controller. And the legacy automotive system from operations management perspective is subject of the development phase. Yeah? That's the static area. Now we are looking also at operations. Now we wonder, yeah, what are candidate management services for each of these phases in that life cycle model. So the coding phase, this is typically what we know from static management. And now, looking at that phases here, there are management services associated to each phase, from the release phase, deploy, operate, and monitor. But what means actually dynamic? We have just seen in the previous presentation some ideas about the notion of dynamic. So first of all, that term configuration management is not denoting the complete area of management. Yeah. So we have split the management activities in object lifecycle operations, create object, delete object, modify. And an object might be every entity subject of management. Might be a service, yeah, might be a software component, or whatever. And then we have also management services related to the retrieval of information, notifications. Notifications are, for instance, are alarms or fault management. And then we have used a color code of blue, red, and green. And in order to have a contrary term to software-defined vehicle, we are using here the notion of a hardwired vehicle. Here, a life cycle model, and here the frequency of management activities. And this is the legacy life cycle model of start of operation, start of production, pre-SOP, post-SOP, and blue, the whole number of management activities you see are subject of the pre-SOP phase, of the manufacturing phase. And during the operation of a hardwired vehicle, there are only a few activities appearing. It's not zero, but it's close to zero. And now in opposition to the hardwired vehicle, the software-defined vehicle, we need a life cycle model of a development phase, an operational phase, development, operation, and so on. Yeah? And if we look on the object lifecycle operations, like configuration management, yeah, of course, the very majority is still during the development phase. But there are also a few ones during operation. So always in the development phase, there are these object lifecycle operations. Green is object notifications, information retrieval. For instance, we are monitoring the system, doing operational state supervision, performance monitoring, data collection. And then another example, this is a special example, this is security management, yeah. So the update of security rules, policy rules is typically done on a daily basis, yeah, for a security gateway. So typically we have activity during the operational phase. So that slide should just illustrate when we are transitioning from a hardwired vehicle to a software-defined vehicle, that the aspect of managing such a systems have a much wider view, yeah? And that transition has an impact, yeah, on the architecture, the management architecture of such an information system. Here, what means actually dynamic, what means time? Of course, we have objects which are unconstrained, which could be managed during the operation, but there, of course, are a lot of constrained objects, like safety constrained objects, security constrained objects, and there will be no management activities on such constrained objects during operation. That's clear. So typically, it's the addition of new features, the deletion of existing features, the hardening of continued features, like in a smart IoT device, like in a smartphone. Now, the proceeding we can't evolve such an architecture on a technical system. We have to step back and look on top of the system. So we have to really to do some model-based systems engineering for such an architecture. And what is our approach we've used? So we are using the modeling framework which differentiates between viewpoints, functional, logical, technical, operational, requirements viewpoint. We've heard in previous talk also that viewpoints, requirements, functional, logical, and physical. Here we use the notion of technical. And operational are the use cases. And the second dimension are system abstraction levels. So here at that end would be an AUTOSAR system, because it's a software system, and a software system is a technical system. But AUTOSAR knows also different viewpoints, at least two. So there's also a concept of a functional logical system. So this is the system at, let's say, the program code abstraction level. We have to go one step on top of it, at least one, and that level would be something like an abstracted EE reference architecture. But due to the fact that we also consider the entire DevOps life cycles, we have also looked at the actors and the activities. So we are looking at that two abstraction levels. And now the challenge is to develop a management architecture which allows the dynamic management for the entire DevOps life cycle for such a system here. And that might be not an AUTOSAR system, it might be also a Jasper system, or every other in-vehicle distributed computing system. So we are going through a couple of these artifacts. There are much more. I may only touch in this talk the surface of that problem. Yeah. So let's start. Starting with the requirements viewpoint. Now, we have also heard already how important the context is, the system context. It's not only relevant for security context, it's in general context. So what is actually the context now in the requirements viewpoint? So the legacy AUTOSAR system as in-vehicle distributed computing and communication system would be here. Now, we have all that entities, sometimes you denote them as resources or objects, which are subject of operations and management. And these entities will be represented by an information model, by a management data model, and there will be a pair of roles added. So we are adding explicitly an agent to the managed system and a manager. Also, there will be an interface between the agent and manager. And this morning in the keynote speech, we've heard something like a generic interface. We have denoted this here as a management programming interface, because we are talking here about management. So we are reusing just well-known, proven ICT patterns from information communication technologies. Nothing is invented here. So first, we are separating the information planes in a user and a management plane. This is not the case today in today's system. Then, with that separation, we got an explicit representation of the entities under management, which leads us to a management data model. And the common management data model is the baseline for an integrated, comprehensive management approach. Then we need a separation in manager and agents. And this is more than the just heard SDN model in software-defined networking. The SDN controller would be here, the manager, but we have also explicit agents here. When we got a management programming interface, and this is an interface which might be locally or remotely, so we need here a protocol. So we want to use here a standard management protocol. not open flow. We recommend management protocols from the NetConf family. And all the services performed here on the managed systems is not only configuration management, not only network configuration, it's actually for the entire distributed computing and communication system. And these are typical categories. Now, let's look on the system context when looking now on, let's say, on an in-vehicle computing system. These are compute nodes. In the middle, we have a legacy AUTOSAR system, so a classic AUTOSAR, adaptive AUTOSAR, but we don't want to provide only a management system for AUTOSAR only, for the entire vehicle, for the entire software-defined vehicle. So also we have non-AUTOSAR compute nodes, and all are interconnected by multiple or single in-vehicle communication network, and that's also part of the management. Here in each compute node we have deployed agents, and now here are the managers. So we are extending the system by an extended AUTOSAR view, vehicle on board and vehicle off board, because we want to support local management, onboard management, and remote management. And in order to get access from a manager to the vehicle, we need something like a gateway, a management gateway here, and that's located here. So this is more or less the system context for such a system. And just a side note, because due to all the discussions about digital twins and digital data sheets, such an ICT management architecture patterns has already that digital twin model included. And this is due to the fact that we have here management data stores at agent level and management data stores at manager level, and they are in relation like a digital twin. So the digital twin concept was nothing new in operating and managing distributed system. Now the picture becomes more complex. Why? We have just looked at the vehicle in operation, the software-defined vehicle in operation, but also we have the phase of development. So we have here the row which denotes the planning phase, the replanning phase. So that system doesn't exist yet technically. We have here the build phase, but we want one manager for all. This is the world of the hardwired vehicle we know so far from management perspective. The software-defined vehicle introduces also that operational phase. Now we don't want to have a manager, a tool chain for that development part, and another tool chain for the operational part. The vision of one manager for all. So this vision is achievable because the representation of that system under operational management, that data model is the same. So we have always here the same model, the same data model for all. Of course, the performance, the functions performed by that manager are different in a planning, build, and operation phase. Now, a further comment to the actors. We have the developer, we have the manager and operator, but we know configuration management is very error-prone. You can do a lot of failures. So what we actually want to achieve is that we want to reduce humans out of that management chain. We want to introduce automation, bringing in machines. So besides the level of automation for driving control, there's also a concept for levels of automation for vehicle management. And this is also known in ICT, so autonomous network management and so on. So what does it mean? It has two conclusions. First, we have from the very beginning introduced machine type of managers in our architecture, even we still fully manually manage our system with level 0. And secondly, the management data models containing information, containing semantic information. And of course, if you use machines, the semantic has to be very precisely specified. And they have to keep this in mind when we are defining data models. Now, what are our goals? And we have the goals split it in two parts. So the first part is we have some paradigm or technology-driven goals. So management architecture, management data models, management protocols. And then, of course, we have existing processes, design, build workflows in AUTOSAR. We have good tool chains, and these we want to continue with the tool chains. Yeah. So just to highlight the goals, so we have to introduce a layering principle, not only in the technical system, we have to introduce a service layering, a functional service layering, in order to partition data models. Then, from a hardwired vehicle to a software-defined vehicle, we have to introduce something like a centralized manager beside distributed managers. And then, of course, from static to dynamic. Data models imply that we have to separate the information plane in a user plane and in a management plane. This separates our data models. So we have application data models and management data models. And then we are proposing to use one data modeling language, and we think for computing system and communication systems, that language today is Yang, which is used in ICT. And this is the example when we are introducing TSN, IEEE 7022, what kind of impact would it have of AUTOSAR RxML? And management protocols, that management programming interface, preferably one protocol family, and then of course if we have a protocol family, we have a reference point, we need protocol profiling. And this AUTOSAR design build workflow goal is how could we integrate Yang into RxML. So it's not one or the other, it's a common approach. Now, the second type of goals, which coming more from the software-defined vehicle side, from an in-service dynamic management. Here now a table which shows in one column the development life cycle, the operational life cycle. So here a software-defined vehicle under development, under static management, and here a software-defined vehicle in operation under dynamic management. And then a vehicle might be in stop phases or might be in motion phases. Yeah, and of course, I'm not performing certain management activities when a vehicle is in motion. Yeah, and stop phase could also mean this is a simulation model. Yeah, so this is more or less the hardwired vehicle where we come from. Yeah, and these are examples for dynamic management, and this, of course, here, that quadrant is the most challenging one. Dynamic management for a vehicle in motion, but just think about monitoring a system, operational state supervision, data acquisition, data collection of such a vehicle. Operational viewpoint, these are the use cases, and we have already heard use cases in the previous session. So again, that table is just indicating example use cases. The first row is the development phase. The second row is the software-defined vehicle in operation. And now the columns is object configuration, object monitoring, object fault monitoring, performance management, security management, quality of service management, and so on. Yeah. So what's the message? Yeah, the hardwired vehicle covers that area here and that area here so far. The software-defined vehicle have to consider everything here, and there are use cases for dynamic part. And just think about fault management. We've heard what what happens if a link fails and so on, or the security stuff. Now, coming to the next few points, we are going now into the functional architecture, and now we have to, the question is, we have today, of course, in AutoSAR, we have data models based on RXML mainly. And if we want to introduce now Young-based management data models, how could we show what part will be Young and what will be AutoSAR? So we have to do some reverse engineering, reverse modeling the entire system, and the vehicle we are using here methodology-wise is a layering principle. Yeah. So the information plane, the user plane, the application plane is here. Here's the management plane. And now we are using here 4 layers, 4 service layers. We are not in the technical viewpoint, we are in the functional viewpoint. The lowest layer is the physical infrastructure services, then the virtual infrastructure services, then the connectivity and data transfer services, so communication, and then the application services. And this is the entire distributed system. Yeah? So these infrastructure services are computing services, storage services, communication services. So we are not looking at network management only, we are looking at the management of the entire distributed system. And of course, the legacy AutoSAR covers so far everything, here, all service layers. And this is just the communication part. And now, from a management plane perspective, we are looking, what are the entities actually under management? What are the objects? And typically, we are belonging to a certain layer. And now, with that layering principle, we could partition the management data model in layer-specific management data. And here the 2 managers, we have already seen that model as well. This is something like the long-term centralized manager, a management manager, and this is the application view, the distributed manager so far. Now, we're looking at Yang and Yang-based management data models. If we would have here physical infrastructure, virtual infrastructure, just look at the network, and connectivity services, this is the world of communications. So this is the world of Ethernet and Internet protocol. This is the world of Yang-based management data models. And why should we reinvent these data models in RxML directly? We want to reuse the data models and integrate them in the AutoSAR world. On the other side, of course, the applications here, like a signal domain, control loops, this is very automotive specific. We keep that in RxML. So the method here is to find out what kind could be Yang-based data, and that Yang-based data would be then mapped on RxML data models. Yeah, and that would be a separate discussion how such an architecture evolves with a distributed manager and a centralized manager or multiple managers. I'll have to skip that discussion here. Now, the question of Yang versus AutoSAR or Yang versus RxML. So here the process in developing AutoSAR system. So firstly, you look at the system level, which means a distributed system of ECUs. Then you look at a single ECU node, and finally you get your individual node. So this is the existing chain, processing chain. And now here at the very beginning, we have here, see here the new part with Yang. So we want to keep the legacy AutoSAR system development process unchanged. We have mature tool chains, which should be unchanged. So no revolution of the process and development tools, no revolution of the AutoSAR system architecture, rather an evolutionary manner. Thomas, do I have to hurry up? Okay. So, and also side comment, this is not specific to AutoSAR, you could also look at other data models. Now, finally, how would such a management architecture look like from a logical viewpoint? And this is, of course, the architecture model is very simple. This is just an exemplification because everyone wants to get that distributed system. So we have here that compute nodes, we have network nodes, we have internally that layers, here 3 instead of 4. We have that agents, we have that managers, we have that programming interface. Yeah. So the message is a single common logical management architecture may actually serve all all the things which I've addressed, and maybe finally mapped on multiple technical deployment systems. So summary. The challenge was to develop for a technical system from a hardwired vehicle, which is in transition to a software-defined vehicle, which has to be operated and managed for the entire DevOps life cycles, not only during the planning and build phase, the development phase, also in the operational phase. And we have developed a logical architecture for such a system at an upper system abstraction level. We've shown how standard Yang-based management data models could be integrated in the AUTOSAR world, and the management architecture, and of course also management protocols. So that was, I think, quite a heavy task as last session for today. So I'd like to stop here. Thank you for your listening.
So thank you, Albrecht. Are there some questions? I think everyone is now overwhelmed with information. So if there are no questions, we will break again, and we will meet 4:30 for our highlight of the day on Bob's interactive session. 4:30 here in the auditorium again. Thank you very much.